Hello everyone. Today we will understand a very famous topic that is known as Fresnel Biprism in the interference. So what is Fresnel Biprism? How it works? What is need of the Fresnel Biprism in the beginning? You know the interference divided into two main category: division of wavefront and division of amplitude. So in the division of wavefront, the famous example of the Fresnel Biprism. So initially the role of this biprism is to obtain coherent light, because whole interference pattern, if we do not have the coherent sources, we cannot define well-defined pattern. So that time there is a need of the coherent sources. So Fresnel is the device, optical device, that is main purpose initially was the obtain the two coherent sources, and later on there are applications how to obtain the wavelength of the given source. So the main purpose of this biprism, the Fresnel biprism, is to obtain coherent sources. What is meaning coherent sources? To obtain coherent sources. Coherent sources. So what are the coherent sources? Coherent sources means the sources have nearly same wavelength, same frequency, but having constant phase difference. Here also phase play important role. So how initially it was constructed? Suppose we have that simply a glass slab, and in that glass slab, we can cut the slab in this way so that its one angle remains your 179 degree, another two are 0.5 degree each. So this is a prism which has in this format, like one angle is up to the angle that is around 179.5 degree. Other two angles are 0.5 degree and 0.5 degree. So how it works? Let's understand the basic diagram, and later on we will understand the how to calculate wavelength of given source. So very famous formula that the beta is called fringe width, and that is equal to d lambda upon 2d. So if we want to calculate the lambda of the given source, the lambda equal to beta into 2d upon d. Now there are three quantities, three numbers, three values: fringe width number 1, number 2 2d, number 3 is your d. If we know the values of fringe width beta and distance between two coherent sources, that is small 2d, and also distance between the source to biprism capital D, we can calculate the wavelength of any given source. So first understand the diagram, then we calculate this wavelength of given source. So diagram is very simple how it works as two coherent sources. Let's understand diagram by first, and then later on we will calculate further values. Suppose this is my biprism. Suppose this is my biprism, and this biprism put in this manner. I mean, there is a central point is there, central point. Now here is the source. A source is single source. Remember, single source can produce two coherent sources. I mean, there is very famous quote कि single source may produce coherent light, but two independent source may not produce coherent light. I mean, single source can produce coherent light. How? This is upper part. Now you can put name of this E, F and G. These are name of that surface. This angle, these are three angles, and this prism put in this way. So suppose this symmetrical part EF and EG are symmetrically. So suppose a ray incident at this surface, upper surface. Okay, what will happen after draw normal? It may go like this. Okay, we can put one arrow. Suppose there are another ray which is incident at the corner, we can show by two arrow. It may go like parallel to this two arrow, and because these two are never met, and suppose this is my screen, this is my screen. So let us understand, when we produce these back and they appear at certain point, that point is known as S1 point. Okay, and this angle, this angle is deviation angle, deviation. So S1 is the virtual source. Similarly, at the lower surfaces, lower symmetrical part, suppose an incident ray here, and after normal it goes like this. Okay, you can show by one arrow. And now similarly there is another ray incident at this corner, then it will go parallel like this. Okay, so again when we produce these two rays, they appear at certain point, that point is called S2 point. Remember, S1 and S2 are two dependent source. They are depends on that S. Suppose there is no S, there is no S1, S2. So they are called dependent source that depends on S. S is called independent source. So distance between these two sources is generally denoted by either 2D or maybe D, and this is my small a, I mean source to biprism, and this is small b, source biprism to screen. Now again remember that D remains same as such. D is the A plus B, D equal to A plus B. So now understand that the central part is there. Now in this part, how that works. I mean, you can put value here. You can say this is P, this is Q. So this is P. So what is the triangle name? This is, let us say A. This is, let us say B. So A, S1 and Q. There are two triangles. To cone you can say A, S1 and Q. And similarly B, S2, B, S2, B, S2 and P, P. So remember that when you're taking the A, S1, Q and B, S2, P. So there is a common portion. This is common portion which is common in both way when you're taking two cones. So this is very important part. Interference is nothing but it is superposition, super overlapping part. You can say this is overlapping part. Overlapping means where two parts are overlapping region. So it is also known as interference region. So interference region is nothing but where two portions are overlapping. So we will get the fringes on this side. We will get alternate dark, alternate bright, dark bright and dark bright fringes on this side. Similarly on the lower half we will get same fringes pattern. So these are called straight fringes. If we call about there are another pattern called Newton rings and Fresnel Biprism. The difference is in the Fresnel Biprism we get the straight fringes pattern and central part of the screen. So now how to calculate the fringe width? I mean, I told you in the previous, if you want to calculate the fringe width, so that is the very basic formula. We need the three measurements. What they are measurements? I hope it is clear, because very simple. Now calculate the wavelength of any given source. That is the one application. So this is very good because we can understand this lab part also. But sometimes what I believe that if theory matches with the practical part, you have the double understanding. I mean, double advantage. What we are reading in the theory and that come in the practical part. So the formula that I wrote earlier, lambda equal to beta into 2D and upon capital D. So in this formula, Remember, there are three measurements are required. So one is the measurement of fringe width. Measurement of fringe width. In the experiment arrangement, we need that sources, we need the biprism, also we need the eyepiece and lenses. They are arranged in the optical bench so that we can obtain easily the fringe pattern. Suppose we are getting fringe pattern, after that we can calculate the lambda of the given source. Maybe example you can say sodium light. So how to find the fringe width of that beta? I told you that we are getting the fringe pattern like this, alternate dark, alternate bright, dark, bright. Suppose this is my fringe pattern that I am getting on the screen. So how to calculate the wavelength, fringe width? Suppose this is my first fringes. You can origin 1, you can 2, 4, 6, 8 and 10 so on. So this is the pattern that we are getting. Maybe we can count the either dark or bright, because this formula is valid for both dark and bright fringes. So lambda will be same. Either you count the bright fringes or you count the dark fringes. So beta can be calculated as distance moved by micrometer. Suppose distance moved by micrometer is, let us say, 10 centimeter, 10 millimeter. And in that 10 millimeter, suppose there are 100 fringes are moved. 100 fringes are moved in the micrometer. So that simple, your fringe width is 1, either millimeter or centimeter, depending on the scale. So fringe width can be calculated this way. Other measurement is the capital D. Capital D is very simple. We can calculate distance between the source to biprism. D is the distance between the source to biprism. Source to screen. Okay, simply measuring through distance on the optical bench. Now third part is very important part. Third part, how to calculate the 2D. 2D is called distance between two coherent sources. Don't confuse 2D. There is a single name. Like how would we write the 2 means we can say d by 2. Otherwise it is combined term, not two separate. Okay. So distance between two coherent sources. So there are two formula. That one formula is 2D equal to 2a mu minus 1 into alpha, and second formula is 2D equal to 2 and the square root of that d1 or d2. So this a is called distance from the source to biprism, and mu is called effective index of that prism. Alpha is one angle. Here d1 and d2 are image heights. So if we know this, is very easily we can calculate, because repeating the experimentally we are doing this part. So by knowing the value of that beta and capital D and small 2d, we can calculate lambda. So lambda will be your that beta, some numerical value, and also that 2d you can put either this or this depending on the measurement, and capital D is something this. So this is the wavelength of given source, maybe sodium source. We can repeat number of times. So there are also a term called lateral shift. Lateral shift means shifting of fringes up and down. This is drawback of that biprism. Sometimes we are not getting the fringes equally on the screen. Sometimes it is too high, too low. So how to obtain that? Just shifting the position of your microscope to and fro, we can obtain we can remove that lateral shift. So basically this is the one example. Numerically or experimentally we can find the wavelength of sodium light. Like sodium, wavelength of sodium light is the 5 lambda equal to 5.8 93 angstrom.